During the past half-century of the greatest scientific and technological development in all history, concrete has had a vital and often spectacular role. New methods of design and handling of material have changed old applications almost beyond recognition, and hundreds of new uses have been developed to meet new requirements. But unlike the horse and wagon, Model T Fords, and baling wire airplanes, which practically disappeared from sight and into museums, old concrete is difficult to demolish and retains a great amount of utility even when it is no longer as attractive nor as functionally efficient as newer construction. It has therefore been possible to film mostly in 1 year, 1965, much of what has happened to concrete in the last 100 years. It is with such pictorial accounts of great change in structures familiar to everyone that we propose to celebrate the amazing advances in the concrete industries during the past 50 years and the golden anniversary of the Portland Cement Association in the United States and Canada. Although there was a lot of concrete built prior to 50 years ago, its uses were limited to rather basic structures: barge canals and locks, seawalls, lighthouses, foundations for barns and factory buildings, coaling towers for steam locomotives, retaining walls and fences, narrow sidewalks and steps, and strips of pavement hastily devised in a frantic effort to keep the automobile out of the thousands of miles of mud that were North America's only roads up to that time. Probably concrete's greatest contribution over the years has been to transportation of all kinds. In fact, it was the great program of cross-country barge canal construction to connect widely scattered navigable rivers and lakes that started intensive manufacture of cement in this continent 100 years ago. Millions of bushels of cement were manufactured in vertical kilns such as these still in use to make small quantities of special cements in Rosendale, New York, to line canal ditches and build small dams and locks. Literally hundreds of concrete locks raised and lowered a constant stream of barges as they traversed the uneven terrain between the Hudson River, the Great Lakes, and the Mississippi, and from the St. Lawrence to interior areas of eastern Canadian provinces. One of the most unusual of these locks was built at Peterborough, Ontario in 1904. It employed a system of counterbalancing hydraulic elevators to raise and lower barges in water-filled chambers a vertical distance of 69 feet in the Trent Canal. Made commercially obsolete by the vast network of railroads early in this century, many of these old locks have only recently been put back into service to move a fast-growing traffic of pleasure craft. But their modern counterparts changed little in design and function, but vastly greater in size, today bring ocean vessels and block-long ore, grain, and oil tank ships through the various levels of the 1,000-mile-long St. Lawrence Seaway system. The transportation of water to supply urban reservoirs and feed irrigation districts was a function of concrete long before paved highways were dreamed of. In 1893, the Gage Canal, lined with a thin plaster coat of concrete, wound through several miles of citrus groves around Riverside, California, setting a new pattern for economical distribution of precious irrigation water. In 1914, Brooks Aqueduct was built to carry a large volume of water on a course both under and above ground to supply a new irrigation district in southwest Alberta, Canada. But the widespread use of concrete-lined canals and ditches did not come until the middle 1950s, when development of special slip-form pavers made fast work and cut the cost of construction to these projects. In 1966, the largest canal lining project ever attempted is the 105-mile-long San Luis Canal at Los Baños, California. This huge waterway, ranging up to 200 feet wide and 36 feet deep, will bring great volumes of irrigation and local utility water from the large rivers of North California to desert areas as far south as San Diego. Today, hundreds of miles of concrete-lined feeder canals bring water from distant sources to local irrigation districts in California, Arizona, Texas, eastern Colorado, and other areas. Here, the water is channeled into thousands of miles of concrete ditches built beside lush fields of produce, which but a few years ago were acres of bleak desert. In the 1960s and for years to come, a major problem concerning everyone in North America is conservation of a limited supply of water in the face of growing populations and daily increased uses of water for all purposes. The storage and control of water has long been a job for concrete. The first concrete dams were small structures to back up streams for mill races. Then came dozens of low-head gravity dams, built in many areas of the country to impound reservoirs for community water supplies. During the first decade of this century, larger dams were built to serve several purposes, including irrigation and production of relatively small quantities of hydroelectric power for communities or private industries. The U.S. Bureau of Reclamation built a small diversion dam in Nevada in 1908. But the first major project of this agency was a 328-foot-high concrete arch on the Shoshone River near Cody, Wyoming in 1910. Now called Buffalo Bill Dam, it was the start of a program which has provided flood control, public and agricultural water supply, electric power, and recreation facilities for people in thousands of square miles of the American West. The wide Grand Coulee Dam in Washington, first major control structure in the Columbia River Basin system, was built in 1937. Other far northwest dams include the new Wells Dam near Chelan, Washington, and Rocky Reach Dam near Wenatchee. Since these Pacific area dams often are located in rivers used by salmon returning to their originating waters to spawn, ingenious concrete ladders have been devised to permit the great fish to leap from step to step up the several hundred feet of structure that bypass the dams. The newest Bureau of Reclamation dams, East Canyon Dam in Utah and Yellowtail on the Bighorn River in Montana, are the latest types of thin arch structures which are rapidly designed for economical construction by electronic computer methods. Although Wilson Dam on the Tennessee River in northern Alabama was built during World War I to provide power for the manufacture of nitrates, the real start of the Tennessee Valley Authority was Norris Dam, built in 1934 near Knoxville. It was the first of the series of water control structures which harnessed the wild waters of the Appalachian Highlands, providing millions of kilowatts of low-cost electric power, creating new recreational areas, and freeing thousands of acres of farmland from the annual threat of devastating floods. The newest concrete dams in eastern U.S. and Canada contrast greatly in size and purpose. Coburn Dam in Virginia impounds water for a town of 2,500 people. 1,000 miles to the north, the largest dam ever built on this continent, Manicouagan 5, is a mile-long, 700-foot-high multiple arch structure. It will control the year-round flow of billions of gallons of water into a system of hydroelectric dams to produce power for the province of Quebec. The Corps of Engineers has long been a large user of concrete for the protection of the nation, first in flood control structures on the large interior river systems, and by a continuing program of seawall construction and harbor protection. A strange significance might be read into one type of the Corps work. In 1899, the engineers built Fort de Soto at the mouth of Tampa Bay, one of many concrete forts for the coast artillery scattered along the east, west, and Gulf shores. These great howitzers were never fired in anger. During the past 8 years, the Corps of Engineers has built hundreds of pads and silos for the launching of nuclear missiles in many parts of the U.S. The whole world hopes that these facilities will, one day soon, be as unwanted for their original purposes as the old coast artillery forts. Hard-paved highways, largest users of concrete over the past 50 years, are the result of the fantastically fast acceptance of the automobile as a premier mode of transportation by a continent full of people always on the go. But the first concrete pavement on record was strictly for horses. In 1893, the village authorities of Bellefontaine, Ohio, ordered strips of grooved concrete laid beside hitching posts in the public square to prevent horses from kicking up a cloud of dust from the crushed rock macadam surface. Later on, towns in Wisconsin, Iowa, and Illinois paved many blocks with concrete because it was cheaper than cobblestones and brick, which required costly hard bases to keep them smooth, and was preferable to the sticky dirt and dust caused by tar and oil surfaces. But the advent of the automobile caught Canada and the United States entirely unprepared. With their spread of thousands of miles between cities and towns, fairly accommodated by canals and a burgeoning network of overland railroads, there had been no need for improved roads any longer than a horse could pull a wagon in one day. That's why the first hard roads and early concrete roads that can still be seen today were narrow, half-width strips running between towns and villages. They served the Sunday tourist and the farmer who needed a road to market that could not be rutted and mired out of use by the slithering auto. The frantic attempt to get the automobile out of the mud saw concrete, brick, crushed stone, and oil used for narrow, hard pavements that, because they were mostly between large population areas, created frightening traffic jams. Even exposed concrete pavements projected on such major overland routes as the 1914 Lincoln Highway, now bypassed by more direct routes, were not designed for easy passing, safe sight distance, or for the heavy rumbling trucks of World War I that would turn much of the continent's supposedly hard pavement back to rubble. The 2 decades of the 1920s and 30s saw the greatest concentrated period of highway improvement. Engineers developed a new science of highway planning for both present and future needs. But few then could guess that there would be a time when 8 million new cars and 1 million trucks would stream onto the road each year, and that the superhighway was more than a wild dream. Such a wild dream had been Coleman DuPont's. He proposed in 1912 that a multi-lane highway with a 200-foot wide right-of-way be built the length of his state of Delaware. His scheme provided for mass transportation at the center, flanked by concrete lanes for opposing streams of auto and truck traffic, and lateral lanes for slower horses and wagons. But it was not a wild scheme. Except for the horse and wagon traffic, it looks very much like the Eisenhower Expressway in Chicago, completed in 1960. World War II also took a terrific toll of North American highways. It proved that something more was necessary to keep its citizens mobile and its far-flung defense lines open and free. A pattern for the future had been set. In 1940, the Pennsylvania Turnpike was built to provide 150 miles of high-speed, high-volume traffic, safely divided by median strips and further protected by controlled points of access. Today, more than half of a vast system of interstate and defense highways that will safely interconnect 55 of the nation's main urban centers has been completed. Thousands of miles of rural expressways now cut through all kinds of terrain and hundreds of miles of urban freeways carry this vast traffic of cars and trucks through and around the great cities and intervening towns. Many of these routes run north to connect ultimately with the Trans-Canada Highway, where in fast-growing, thickly populated areas such as Toronto, Ottawa, and Montreal, they are building traffic routes comparable in design and use to those in the U.S. Advanced methods in concrete paving construction, new equipment, and highly trained men now make it possible to pave 1 to 2 miles of 24-foot wide roadway a day, and do it day after day. In many areas, paving costs are reduced by the slip form paver, which, with relatively small personnel and no forms to set and remove, produce some of the smoothest concrete pavement in the whole highway system. Because the interstate system of highways must run free of intersecting traffic, it is estimated that 1 new bridge per mile of highway must be built to go over and under intervening crossroads. These are far different structures than early concrete bridges. The first reinforced concrete bridge in the United States was built in Rock Rapids, Iowa in 1893. It was 16 feet wide and cost $830 to build. A year later, another concrete arch bridge was erected in Edens Park, Cincinnati, Ohio. It had a 70-foot span and was 75 feet high. The Tunkhannock Viaduct of the Erie-Lackawanna Railroad near Nicholson, Pennsylvania, built in 1915, was startling not only for its sweeping, many-arched grandeur. Its half-mile span over a wide valley eliminated dozens of miles of track, at least 20 grade crossings, and reduced up and down grades totaling 327 feet. During the 1920s and early 30s, the bowstring arch was a useful and economical, if not always spectacular, bridge design in many areas. The most unusual bridge of that period was the first of the concrete pontoon, or floating bridges, over Lake Washington near Seattle. Large, hollow boxes of concrete, 350 feet long and 5,000 tons, were cast, then floated into position and connected to form a long, water-supported structure. Washington State has 3 of the 5 such bridges in the world and plans to build another. Walnut Lane Bridge near Philadelphia in 1949 was the first pre-stressed bridge in America, employing the technique of putting the girders under longitudinal compression by stressing high-strength steel cables running through channels. This historic structure, which may look a bit over-designed in view of later developments, was the young father, if not the granddaddy, of many of the interstate bridges today. But the most exciting pre-stressed bridges this year of anniversary are in Canada, where there is great space and great need for long-span bridges. One of these is the Hudson Hope Bridge, a hollow girder, concrete deck structure suspended on cables and pre-stressed over its entire 680-foot length. A high, slim, graceful bridge spans a broad valley along the Trans-Canada Highway near Kennard, British Columbia. It cuts, fortunately, through some of the most delightful scenery in the Northwest. Waiting to carry an expected stampede of millions to the Montreal World's Fair and Exposition of 1967, Senville Bridge, spanning the Ottawa River, has just been opened as a much-needed link in the Trans-Canada Highway from the west. Rapid changes in the way we live and work has made concrete essential to other forms of transportation. Today, commercial jet aircraft, heavier than the steam locomotives of bygone years, take off and land on long concrete runways. These are huge earth-supported beams, often 1 to 2 feet thick and up to 2 miles long. To bring mass transportation to fast-growing, vehicle-crowded urban centers, many city planners are considering monorail structures, such as this one, built for rapid transit needs during the recent Seattle World's Fair. To reduce some of the large costs involved in railway track construction and maintenance, There has been a revival of interest in the use of pre-stressed concrete cross ties as a replacement for wood. During 1965 alone, more than 100 miles of mainline track in the U.S. and Canada were converted in this manner. The farmer has always been involved in concrete. The early barge canals and the first half-track pavements were built to move agricultural products. As a handyman, the farmer often mixed his own concrete for fence posts, pump platforms, watering troughs, and foundations for his outbuildings. There were some notable concrete farm showplaces, such as the 8 connecting Pabst farms near Oconomowoc, Wisconsin, built between 1907 and 1913. But in the main, the North American farmer adapted concrete to his needs and developed his own particular uses to fit very special requirements. The first silos were square or cylindrical structures made of rubble stone held together by large quantities of cement mortar, which was also used to plaster the inside. Because so much concrete was required on these tricky masonry walls, some genius decided to make it entirely of concrete. And this is how it looked, and still looks. One builder has erected hundreds of silos since 1915 in eastern Pennsylvania. Here is one of his 50-year-old cast-in-place silos near Shippensburg, and one of the modern concrete silos he has erected for dairy farms in recent years. In the 1930s, the first concrete feedlots and floors aimed at taking farm animals out of the usual barnyard mud and filth were found to save hundreds of hogs and cattle from fatal diseases and also save bushels of grain feeds. Hog raising is a science carried on in factory-efficient concrete barns. Today, while more and more family farmers continue to leave the land, food production of all kinds increases. In the 1960s, farms are industrial plants. Beef cattle now are taken sooner from ranch pastures to be fattened on mile-long concrete feeding floors. The modern dairy is a production line operation, starting with breeding stock, pampered in clean, well-lighted stock barns. Milk cows are kept in spotlessly clean stall barns or loose housing areas. They exercise or loaf on acres of concrete feeding floors which are kept clean of manure by mechanical equipment and are washed down by high-pressure hoses. On the modern farm, old wood and metal outbuildings are being replaced with fire-safe tilt-up and frame buildings that house expensive equipment and complex automation lines. To efficiently feed these great production lines of farm animals, the old silo has had to grow higher and wider. The largest silo built to date, 60 feet wide and 60 feet high, can store the silage crop of 300 acres. Despite their industrialization, many of the great farms retain their rural charm, but fewer people see them these days. We have held our review of concrete houses and building until last, because the use of concrete for dams, silos, and pavements developed sooner and faster than for architecture. In fact, only during the past 15 years have a whole series of technological advances and new concepts in design permitted architectural concrete to break out of plain, colorless forms to creations of startling beauty and size. Concrete was a new material without the 2,000-year-old traditions for marble, granite, and brick, so early builders tried to copy classic forms in concrete. The first reinforced concrete structure in America, built as a home by William Ward in 1874, was a conglomeration of Greek, medieval English, and 18th century French architecture. So convinced were many that concrete was primarily a substitute for stone masonry, they developed a block with one face molded to resemble rough-cut stone. Thousands of rock-faced block houses and small commercial and industrial buildings were built everywhere, but architects thought it horrible. Frank Lloyd Wright designed and made his own blocks, but he did more to create a character for concrete by molding structure and decoration together in new monolithic forms for his Unity Church in Oak Park, Illinois in 1905, and the Barnsdall House in California a few years later. Thomas A. Edison, with boldness but less art, conceived of casting complete concrete houses in reusable metal forms. His prototype homes in Union City, New Jersey in 1910 were rugged and durable, but never attracted much attention elsewhere. The Ingalls Building, erected in Cincinnati in 1902, was the first high-rise concrete frame. But its heavy weight, due to massive columns, thick floors, and envelope of stone, appeared to doom concrete to far less lofty heights than lighter steel frames could achieve. Two concrete buildings erected 50 years ago might have speeded up the use of concrete in architecture had they then been more accessible and better known. Fonthill, a hobby castle, and Bucks County Museum in Doylestown, Pennsylvania, were designed and built by Dr. Henry Chapman Mercer, a museum curator who thought he could do anything with plastic concrete that he could think of. He designed his structures from the inside, molding walls, columns, arches, and vaulted floors together in a sculptured monolith that proved that concrete can combine structure, form, and decoration all at once. The first extensive use of concrete by architects came during the 1920s and 30s in California, where a series of disastrous earthquakes demolished many brick and stone masonry schools, churches, and public buildings. These monoliths were at first traditional in design, but far better executed than before. Expert concrete technicians developed on these projects soon spread out all over the U.S. so that by 1940, architectural concrete was becoming visible nearly everywhere. This new work included such novelties as an inch-by-inch reproduction of the Greek Parthenon molded in concrete in Nashville, Tennessee. Structures of great size like the many-ringed Pentagon in Washington, and designs foretelling great changes to come in form, texture, and decoration of concrete. In the past 15 years, concrete buildings have changed their style and appearance almost beyond recognition. Rigid shapes have been replaced by articulated walls that curve and sweep. Roofs have assumed new forms of domes, gracefully curving barrels, soaring saddles, spreading inverted cones, and combined forms that blend roofs and walls into single, delightful enclosures. The surfaces may be as smooth as cream or heavily textured, pierced with 1,000 openings, or delicately sculptured. The once monochromatic exteriors have been banished in favor of delicate shades of subtle color from natural materials, wildly colorful, or gleaming white. Interiors are spacious, sweeping, and flooded with natural sunlight. Those old, monotonous, lumpy concrete blocks are gone, and new masonry products of vigorous texture, sculptured faces, thin, pierced, and lacy, and always colorful, produce both large and small structures of startling originality. Concrete houses are no longer dumpy, colorless stereotypes of all other houses. They are original in design, personal shelters, compact, rambling, or bizarre and startling. This amazing revolution in concrete design and use is the end result of years of study and experiment in which new technology, new products, and new concepts came to fruit at the same time. Portland cement, now made in plants and mills that are models for precise operation and quality control, is produced in a variety of types as required for special uses. Methods have been developed to manufacture aggregates that are but 2/3 the weight of stone and sand, permitting larger structures composed of lighter columns, walls, and floors. Precasting plants are organized and staffed to produce concrete panels of any proposed design and in any size, up to 3 stories high. The pre-stressing industry fabricates columns, beams, and girders of any required length, and concrete pipe units as long as 120 feet. Special high-strength steels fabricated in strands and packed in conduits for easy handling have been developed for pre-stressing use, permitting the casting of longer, lighter weight columns and beams. The great ready-mixed industry provides concrete of any specification, any time of day or night, and for use on projects in widely scattered areas. This has banished the old problem of setting up mixing equipment on the site and stockpiling tons of stone and sand. And above all, because they raise structures under them as they climb upward, are the new cranes that lift and move materials anywhere on a building, and new towering ground cranes that can lift a form for a whole room and set it in place with speed and precision. All these developments are responsible for concrete's startling reach for the clouds. In a mere 7 years, reinforced concrete frames have left their old height limitations far below. Executive House in Chicago was the highest concrete building in the U.S. in 1959 at 371 feet. In 1960, the Bank of Georgia in Atlanta took the American record with 391 feet. 2 years later, in 1962, Chicago's Marina City Towers took a mighty leap to a world record at 588 feet. But this fantastic structure held its dominance for but 1 year, because in 1964, the Place Victoria in Montreal soared to 624 feet, only to relinquish it last year to the 1000 Lakeshore Drive building in Chicago at 640 feet. There are now proposals for heights more than 100 feet above this. There will be a limit, of course, but that will be decided by architects, engineers, and the ever-developing technology in concrete that seems to make everything possible. Meanwhile, the future of concrete in every area of endeavor is going now, from British Columbia to Philadelphia, from Arizona to Montreal. In fact, everywhere you look,